In this session, we will learn how to use the sasviya.ml Python package in SAS Viya Workbench to build and evaluate machine learning models. We will also use some utility functions from the scikit-learn package to help with building the models. This tutorial is designed for Python programmers with some experience training machine learning models, but does not expect you to be an expert at machine learning. If you are interested in seeing machine learning examples in SAS Viya Workbench using the SAS language, we have a separate tutorial video on machine learning with examples using SAS procedures. If you have experience using the scikit-learn Python package for machine learning, you will likely find the materials in this tutorial to be quite familiar. If you have access to SAS Viya Workbench, I encourage you to follow along with me. The SAS Viya Workbench Quick Start repository provides access to the notebook used in this demonstration. I'll start by opening Visual Studio Code in my SAS Viya Workbench environment. Once my Workbench boots up, I'll open up my Python notebook, getting started with Python sasviya.ml for machine learning. To make this notebook more portable, we start by downloading data from a web URL using the Python requests package. We define a file location in the SAS Viya Workbench where we want to save the CSV. In this case, in the workspaces/my folder/machine learning folder. And we want to save the file as hmeq.csv. We download the data from a SAS documentation page and use the requests package in Python to write the URL content to a CSV file. The workspaces/my folder location was created when we initialized our Workbench environment, and we just manually added the machine learning folder using the VS Code interface. Although we will be using SAS Viya Workbench machine learning algorithms, this tutorial is all in Python, so we will use pandas and scikit-learn to help load and prepare the data for machine learning. The SAS machine learning algorithms all live in the sasviya.ml Python package, and we will import them individually as we use them. We import pandas and read the CSV file into a pandas data frame named hmeq_df. SAS Viya Workbench includes commonly used Python packages for data science, and in general, you can use pip to install your own packages, although the right permissions and available packages will be determined by your site administrator. In this tutorial, we'll mostly use pandas and scikit-learn to prepare and evaluate our machine learning models. We didn't have to pip install these packages. They were already included as part of the configuration of SAS Viya Workbench. Before we start building models, let's quickly build a little bit of intuition about this data. This is fictitious financial services data. We operate a bank, and we must decide whether to accept or reject loan requests from customers. Our target in this data is the variable bad, or binary applicant default, and it indicates whether our historical customers defaulted on their loan or not. Here, bad equals 1 indicates that the customer did default on the loan. Bad equals 0 indicates they did not default on the loan. The rest of the variables in the data represent information about the customer collected by the bank, which can be used as candidate input variables for our machine learning models. These input columns contain information like the amount of home equity loan the customer is requesting, the amount left on their mortgage, the value of the mortgaged home, the reason they're requesting a loan, their job, their years on the job, along with some information about their past credit history, like the numbers of derogatory credit reports and delinquent credit lines. The important thing about this data from a technical software perspective is that we have a mix of interval variables like loan and mort due, along with categorical variables like reason and job. In our data, these variables contain strings. We don't have to do any dummy coding when using the sasviya.ml package, but the SAS machine learning models will treat the categorical input variables different from interval input variables. We use the head method to print out the first 10 observations in our data set. Looking at these 10 printed rows, we can see that we have some missing values in the data. In Python, coded as numpy nan values. We want to do something to replace these missing values. Otherwise, the rows with missing values won't be included in our machine learning models, which can dramatically reduce the amount of data we have available for training the models. Imputing these missing values will be a part of our data preprocessing, which is our next step. I will mention up front that this is really the most basic preprocessing that I would do for machine learning, the bare minimum. There are lots of data preprocessing methods available in Python packages and SAS Viya Workbench that could be useful with different kinds of data. And in general, when you're working with new data, it's recommended to spend some time on data exploration, which can help better identify what kind of data preprocessing would be useful. For this tutorial, we will stick with simple data preprocessing, which will include partitioning the data, imputing missing values, and selecting relevant input variables. Partitioning the data into training and validation samples is a best practice that you cannot skip in machine learning. If you don't have a validation sample, you can't really know if you have fit an effective model or if the model has just memorized the historical data used for training. We impute missing values. We do have a lot of missing values in the data, and we want to use as much of the data as possible. Automatic variable selection is more useful when you have a lot of hard to understand input variables. In this case, we only have 12 easy to understand input variables in the data set. But we include it in this tutorial because it can be useful to compare your intuition about what variables might be useful in predicting the target, kind of manual variable selection, with the results of data preprocessing routines that automatically select variables. We split the HMEQ dataset into training and validation samples using the train test split function from the scikit-learn model selection package, sampling 30% of the data as validation data and the remaining 70% as a training set. Scikit-learn expects us to split the inputs from the target, so we create a data frame X containing only the inputs and a data frame Y containing the target bad. We apply the train test split function to these data frames, specifying that we want a 30% test sample for the validation data and that we want to stratify based on the target variable. This stratified sampling means that we will have the same proportion of bad equals 1, people who defaulted on their loans, in the training and validation data. These samples are supposed to represent the data our machine learning model will encounter in deployment, so we should preserve the target distribution from the original data set. We also specify a random state to ensure that the sampling is reproducible when we run this notebook multiple times. This process outputs 4 different pandas objects: 2 data frames containing training and validation inputs, xtrain and xvalid, and 2 series containing training and validation targets, ytrain and yvalid. After the partitioning, we have a bit more than 4,000 training observations and a bit fewer than 2,000 validation observations. Now that we have built this partition, we can start using the training data to build models and do our data preprocessing, while remembering to apply all of the data preprocessing steps to the validation data. Our first form of data preprocessing is to impute missing values, but we want to use the training data to calculate the median and the mode that we're going to use for imputation. And then we're going to use those values when imputing the validation data. The idea is that it's cheating to use information from the validation data to impute values on the training data, since information leaks from the validation sample into the training process. We need to learn our parameters from the training data, but the median and mode that we use for imputation can be thought of as model parameters associated with data preprocessing. This is also more reflective of a deployment scenario, where we will also use the median and mode from the training data to impute missing values in new observations that we want to score. We import the simple imputer function from the scikit-learn.impute package, and we create two imputer objects, one for the interval variables that imputes using the median, and one for the nominal variables that imputes using the mode. Most frequent is the term used by scikit-learn. For both imputers, we set the output to be a pandas data frame, which is not the default for the imputers. This will be important later because the sasviya.ml algorithms are easier to use when our data is in the form of a pandas data frame. In both cases, we use the fit method on the training data to learn the imputation parameters, in this case just the median and the mode for the columns with missing values, based on the training data. It is important to separate the interval and nominal variables for this, so we use the select-dtypes method to ensure that the median imputation is calculated for the numeric variables and the mode imputation is calculated for the textual variables. This could be a bit more complicated if you have nominal variables with numeric values, at which point it could be helpful to create lists of input variables separated by how they should be treated. Fitting the two imputer objects that we created just learns the model parameters from the training data, but we must also apply the imputation to both the training and the validation data. We do this separately for training and validation data, for each sample concatenating the input interval variables with the input nominal variables into a single data frame. At the end of this process, we still have the same size training and validation samples, but this time the 12 input columns have no missing values. We also have the imputer objects that we can use to apply the imputation to new data during the scoring process. Variable selection is important for ensuring that machine learning models are provided useful inputs. You can always select important variables based on subject matter expertise, but it is often helpful to compare your intuition to an automatic variable selection approach. We import the select-k-best function from scikit-learn to select the top 8 most relevant interval variables based on a chi-square test. We only have 10 interval input variables, so this will drop the 2 interval variables that are least useful in predicting the target. Scikit-learn requires categorical variables to be dummy-coded, often using one-hot encoding, before they can be used for most machine learning and data preprocessing tasks. But the sasviya.ml package allows us to skip this step. So we'll just leave our categorical variables in the original form for now. For this example, we will just keep the 2 categorical variables as inputs and select the 8 best interval inputs using select-k-best. Just like before, we want to output a pandas data frame. And once we select variables based on the training data, once we fit the select-k-best method, we apply the variable selection to the interval variables in both the training and the validation data. After reducing the interval variables, we concatenate them back with the categorical variables to get the preprocessed training and validation input samples. This time, these samples only have 10 columns, since we've eliminated 2 of the variables. We also print out the selected variables, but we don't apply any variable selection to the categorical variables, so we selected both without doing any calculations. We can now use these preprocessed input samples to fit our machine learning models with training data and evaluate and compare the model's performance with validation data. The sasviya.ml package is designed to integrate with scikit-learn. So the sasviya.ml model objects have the same syntax and most of the same functionality as the equivalent scikit-learn model objects. The major difference is in the execution. The models in the sasviya.ml package execute using optimized SAS libraries, which takes advantage of multi-threading and can yield much faster runtimes than the equivalent models in scikit-learn, especially for big data. The sasviya.ml syntax is nearly identical to the scikit-learn syntax. The constructor is the same, the objects have the same methods like fit and transform, etc. So if you have experience building machine learning models in scikit-learn, you can easily start building models using sasviya.ml. One convenient feature about this design is that you can take existing scikit-learn code, and without modifying the actual code, you can change the import statement to point to sasviya.ml instead of scikit-learn. This will use the optimized SAS libraries for machine learning without requiring you to do any code rewrites. One difference between scikit-learn and the SAS Viya ML package to keep in mind is that the scikit-learn models require all inputs to be numeric, so we must dummy code before sending data to the model, whereas the sasviya.ml models are designed to do the dummy coding for you if you provide categorical inputs. This is a convenience feature, so all of your legacy scikit-learn code will work with sasviya.ml, but you can skip a few steps in code when using the SAS optimized libraries. The rest of this notebook will look just like a scikit-learn demo, but I will import the models from sasviya.ml instead of from sklearn. I mention this because if you have experience with scikit-learn and would prefer to organize your code differently or use features like sklearn pipelines, you can easily import your scikit-learn code into SAS Viya Workbench and modify it to use the optimized SAS algorithms. Let's start building some different machine learning models, always making sure to compare to a simple logistic regression model. I don't really think of logistic regression as a machine learning model, but it's always a good idea to compare our complex nonlinear models to a simple linear model. I import the logistic regression object from sasviya.ml.linearModels, and I use the constructor to instantiate a logistic regression object named logreg. I accept most of the default settings for the logistic regression model, specifying that I want to use the LBFGS method for the likelihood maximization, with a convergence tolerance of 10 to the negative 4 and a maximum of 1,000 iterations for the LBFGS solver. These settings are all about how the model estimates the parameters, but there is an option for choosing a variable selection method like backward or stepwise for the logistic regression model. After constructing the logreg object, we can apply the fit method to the training data, xtrain final and ytrain, to create our model. After the fitting process, the logreg object can be used with the transform method to score new data, which we will do later in the notebook when we evaluate model performance on the validation data. Also, just notice if we look at the type of the logreg object, it is a logistic regression object that comes from the sasviya.ml linear model package. We can do the same thing with the decision tree model, importing the decision tree classifier object from sasviya.ml.tree. We use the constructor to instantiate the model object dtree, and this time we specify some key decision tree hyperparameters. We use the chi-square method as the split criterion, which is how we evaluate the quality of the splits in the decision tree. We also specify a max depth of 10, so any leaf node in the tree is no more than 10 splits below the root node. A smaller max depth leads to a simpler tree, which can be useful to avoid overfitting, but can also lead to a model that is too simple to represent the training data. Just like with the logistic regression model, we fit the dtree object using training data, and we will use this same object later to evaluate performance on the validation data. Next, we create a random forest model by importing the forest classifier object from sasviya.ml.tree. A forest model is an ensemble of individual decision trees, with each tree fit to be slightly different from the other trees in the forest. When we create the forest model, we specify some hyperparameters related to how individual trees are grown, like max depth, criterion, and minimum samples per leaf, min samples leaf. These hyperparameters are the same as the ones we would use with the individual decision tree model. But we also specify hyperparameters associated with how we create the forest, like n estimators and bootstrap. The forest model is only useful if the trees in the ensemble are different from one another. So we set the bootstrap options to 0.6 so that each tree is fit using a random sample with 60% of the training data. Once we use the constructor to define the model hyperparameters, we can fit the forest object using the training data. We can also fit a gradient boosting ensemble model, where instead of fitting a forest of independent trees, we fit a sequence of trees where each tree tries to improve on the performance of previous trees. The constructor for the gradient boosting classifier object has many of the same hyperparameters as the forest and decision tree models, along with some options specific to creating the sequence of trees, like the learning rate hyperparameter. Notice that with this model, we use a much smaller max depth than with previous models. In general, gradient boosting models are often more powerful and accurate than individual trees, but this comes at the risk of overfitting the training data. We use a small max depth for this model to help ensure that we don't memorize the training data. Once we construct the gradient boosting object, we fit it using the training data. Finally, we fit a support vector machine model, in this case a support vector classifier or SVC model, which we import from sasviya.ml.svm. For binary targets, this is normally a linear model that finds a hyperplane to maximize the separation between the two different classes of the target variable. In this example, we use a nonlinear kernel, the RBF or radial basis function kernel, which projects the problem into a higher dimensional space and then fits a linear hyperplane in this projection. In the original dimensions, this becomes a nonlinear decision boundary. In addition to the kernel, we specify the penalty parameter C, which determines a cost penalty for incorrectly classified cases that show up on the wrong side of the decision boundary. Once we create the SVM object, we fit it using the training data. Now that we have fit our 5 different machine learning models using training data, well, really 4 machine learning models and a logistic regression as a baseline comparison, we can evaluate the performance on validation data and choose a champion model. We didn't spend much time discussing the details of the models or their hyperparameters in this tutorial focused on SAS Viya Workbench, but if you want to learn more about these machine learning models, we have other tutorial videos and even full courses dedicated to the details of machine learning algorithms. The example we show in this notebook uses a binary target, but each of the models we used also has an option for data with a continuous target. For most of the models, we have a regressor option. So instead of using the forest classifier model, we would use the forest regressor model for a continuous target. More details about these regressor models are available in the SAS Viya Workbench documentation. To evaluate model performance and ensure we don't overfit the training data, we score both the training and validation data using all of our models. First, we create a list of models with the name of the model on the list equal to the name of the model object we created during training. We then create an output dictionary for training and validation data from these models. So we have a place to store the scored training and validation data. We use a Python for loop to loop over the list of models, generating the predicted probabilities using the predict_proba method applied to the model object. We join these predicted probabilities with the true value of the target and save the scored output in the model dictionary. We do this separately for training and validation data to yield 2 output dictionaries, each containing data frames with scored output for each model. We plot the ROC curve by using the ROC curve function in the scikit-learn.metrics package to calculate ROC information. Once again, we create empty dictionaries to store ROC information, and then we loop over each of our models, adding the ROC curve information for each model to the pyplot object that we created just a moment ago. We do this separately for training and validation data, so we can compare models on both partitions. There are plenty of other assessments we could use, and we could also use other Python plotting packages like Seaborn. Here we'll stick with Matplotlib. Looking at the results, we can see that the gradient boosting model is the champion model on both training and validation data. And although the performance is better on the training data, we don't see major evidence of overfitting. The validation and training curves seem similar in the plots. Before we declare the gradient boosting model the final champion model, let's look at the misclassification rate at the 0.5 probability cutoff. This isn't necessarily the best cutoff for all models on all data, but it is a good place to start when building and evaluating models. We import the accuracy score function from scikit-learn.metrics, but before we can apply it to the output classification scores, we have to apply the 0.5 probability cutoff to the predicted probabilities generated earlier using the predict-proba method. We could have used the predict or transform method to generate these class values instead, but it's helpful in this tutorial to explicitly choose a cutoff, mainly so I can emphasize that the cutoff affects the outcome and has an impact on the misclassification rate. We use Python list comprehension to create a list of class predictions on the validation data, and then we apply the accuracy score function to this list, comparing it to the true value of the target. Of course, we print the misclassification rather than the accuracy, so we see that the champion gradient boosting model is incorrect for about 9% of the observations in the validation data. The last step in our tutorial is to start thinking about model deployment. To deploy these models, we just need to apply the data preprocessing, in this case just imputation, and the champion model to new data. It's easy to score new cases in the same SAS Viya Workbench environment. We just keep the trained data preprocessing and model objects in memory and apply the transform and predict methods to the new data. It gets a bit more complex if we want to deploy to a different environment. In this case, we would want to pickle the Python model objects by saving them and then unpack them in a different environment. We have learned how to build and score optimized models using the sasviya.ml package. If you want to learn more about SAS Viya Workbench, please see the other videos in this series.